Good afternoon, everyone. Welcome to our seventh Tech Talk of the year and part 2 of our Embodied Carbon and Climate Change series. For those of you here last time, Will Arnold from HQ presented about just sort of an overall picture of the state of play, I suppose, at the moment with the climate crisis, and what we as structural engineers can be and should be doing in broader strokes. And I know he spoke about the embodied carbon factors that we need to start looking at in our calculations, but that was very generic and with a global view. So part 2 now, we're going to start focusing on local information, and team from Arup who are going to present now have done some research around quantifying embodied carbon values across the content, and they're going to give us some insights onto the work they've done and some valuable input, hopefully, as to how we can bring these into our working lives in South Africa and on the continent, and why it's important that we have local data like this. Just a quick introduction. Tessa, Alex, Fiona, and Suvarna form a little team of structural engineers and architects based all over from London to Cape Town and Durban. And I think their focus really is on the sustainability and the climate side of stuff. Please correct me if I'm wrong. I'll now hand over to Tessa, who'll take it away from here. Thanks very much. I look forward to it. Sorry, just last bit of housekeeping. We're going to say 5 to 10 minutes at the end for questions, but if you have any questions, please write them up in the chat box and we'll deal with them at the end. Thanks.
Great, thanks, Chris, and hi to everyone on the call. Thanks for joining for this really important topic. As Chris said, while I share my screen, just give me 5 secs. Has that shared successfully? Okay, I see a thumbs up, great. So as Chris said, we are going to be talking today about the structural engineer's role in addressing climate change and embodied carbon. This is the second part of a 2-part series where Will Arnold spoke last week. So once I can drive the PowerPoint. So Will spoke not last week, I guess a few weeks ago at this stage, with a really fantastic introduction to the impact that structural engineers can have for climate action. It's really such an important topic, and I really want to stress the role that the structural engineers can play. And I would say that if you haven't listened to that, please do so. We've put a link in this talk, but equally I'm sure that Chris and his colleagues can put that in the chat of this as well, because the recording is available online. So I'd encourage everyone to listen to that if you have not already. So today we're going to be doing a little bit of scene setting, just reinforcing some of the messages that Will gave last week, as well as then going through the unique content for this talk, where we'll be talking about some embodied carbon calcs that we've done for projects in South Africa. We'll then be talking about country-specific carbon factors and why that's important. And then we're going to talk through some of the research that we at Arup have done for location-specific carbon factors for 5 countries in Africa, but we'll just be using some examples from that. Then we'll talk a little bit about some examples and some guidelines around where are the best opportunities to cut carbon. And then we're going to talk about, well, what next? What does that mean for all of you and all of us working in industry during this important time where climate action is so critical? So today we've got Suvarna, myself, Fiona, Maureen, and Alex talking. Suvarna and Fiona, Alex are all based in South Africa. Maureen is in Nigeria, and I am operating between the UK and South Africa. So a little bit of an introduction to the carbon assessment process. This is this is a described and defined workflow that is described in many places. RICS, for instance, has a really good workflow, as does the iStruct. All of this information is available online, and we'll give some links later on. But in essence, what this process does is measure whole life carbon And within that, we have all these words: operational carbon, embodied carbon, and other related words that do have a risk of becoming jargon. What we're going to talk about today is in fact the embodied carbon component. So that is looking at I'm not going to use all of the letters because you can see it on the screen, but in essence, what that is looking at is the materials, where they come from, how they are transported to site, and how they're installed on site. So in terms of this jargon busting, because we all have there's a big risk of lots of words that we don't understand necessarily. When we talk about carbon emissions in this setting, the word carbon has become a jargon word, although carbon clearly is an element, and that is something that's real. When we speak about it in this decarbonization setting, it has become jargon and should be viewed as interchangeable with greenhouse gas emissions. So that's GHG in short. Carbon just has become an easier word to throw into sentences and to words. So what that is the emission of gases, including carbon dioxide, methane, and water vapor. And this is measured in carbon dioxide equivalent units. So when you see this little series of letters here, really that's GHG as well. Whole life carbon then takes into consideration all of these GHG emissions and removals, considering operational and embodied carbon over the life of an asset, including its disposal. So if we look back at this diagram here, whole life carbon is considering every single one of these pieces here. Then in terms of embodied carbon, what that refers to are the greenhouse gas emissions associated with the materials and constructions processes from A1 to C4 on that diagram that we had earlier. And operational carbon, this is the focus of structural engineering, because basically this looks at the materials in the building, the materials that are used to build the building. Whereas operational carbon really is the realm of our mechanical, electrical, and public health or wet services colleagues. And that looks at the greenhouse gas emissions that arise from the energy and water consumed by a building in its use over its life cycle. So that's operational and embodied carbon. In terms of the embodied carbon decision-making, Will did show this decision-making tree in his talk a few weeks ago. Essentially, as structural engineers and our role in influencing the design process, we need to be very cognizant of when we are building, why we are building, and what we're building. So if we start off just asking the question of ourselves, do we need to build anything? Then we need to think, well, how much do we need to build? Then we think about building clever. Then we build efficiently. And as a last step, we minimize waste. So it's really important just to remember that, because the biggest impact that we can have as structural engineers is actually by building nothing. So we all need to be asking these questions very clearly of ourselves, our design teams, and our clients. It's also a reminder that the biggest impact that we can have is at the beginning of a project. As we go down the project process, clearly we can have an impact every single step of the way, but the impacts right at the beginning will be the biggest ones, and the ones with the most impact. So the earlier our engagement is, and the earlier we start asking these questions, the better the outcome will be. I'm going to hand over to my colleague Suvarna now. Suvarna, over to you.
Thanks, Tessa. Hi everyone, my name is Suvarna Maharaj. I'm a structural engineer. I've carried out structural carbon calculations on a few projects so far, and I'm going to run through the basic calculations and processes I've used to do this. I want to stress that performing the actual calculation is relatively simple, but the impact that it has on decision-making is large. Next slide, please. I will be going through the workflow of stages A1 to A5 only, which are the carbon emissions due to the material cradle to gate life cycle, plus transport and construction waste emissions. This has 4 steps to it, which is the input, calculation, output, and most importantly, benchmarking. Once calculations are done and benchmarked, they can then be compared and recalculated to improve on at regular design stages. Next slide, please. The input is in the form of material volumes. This includes elemental volumes of the substructure and superstructure. You can perform this at early scheme design stages and simply involves obtaining volumes for different materials used. This can be done in a few ways through manual calculations and spreadsheets by multiplying the material volume by its density to obtain a mass in kilograms. If you have a running model, you can extract volumes from modeling and analysis softwares. And if your project is quite advanced, you can obtain actual data from quantity surveyors. The data does not have to be accurate, especially at scheme stages where hand calculations are common and quick, but the idea is to perform it as soon as possible so that you can compare it to others. Next is the actual calculation, which involves multiplying the mass of the input data by its respective carbon factors to produce stage A1 to A3 cradle to gate results. I've based my calculations thus far on UK factors because I don't have readily available local factors. And we'll talk a bit more about this, the local factors versus international factors later on in this talk. But not possessing local factors should not deter you from performing the calculation. Factors are relatively similar and many are based on international best practices. Each material volume is then multiplied by a transport emission factor and construction waste factor to obtain stages A4 and A5. I can then obtain my output in the form of a total carbon tonnage and divide this by the project gross internal flow area to get a value per meter squared. The gross internal area, and I'll call that GIA, includes all areas that are within internal walls and partitions and excludes balconies, parking, and walkways that are open areas. I'll post a link at the end of this for guidance on what is and is not included in the GIA. Once I obtain the output, I arrive at the last step, which is benchmarking. I can then save my data and share it and use similar projects that are similar in nature to compare it to. The goal here is to grow my database of carbon calculations so that I can gauge the impact my project has compared to others, which help guide the decision-making process going forward. I can also rerun the calculation when structural systems are explored or investigated. For example, comparing structural steel floors to concrete and using the carbon impact it has to guide my end result, my end choice. At very early stages, the carbon calculation can also be done for a single grid panel also. Next slide. So now I'll run through an example of a residential building I did recently at tender stage. The site contained 3 apartment blocks, but for now the calculation is based on block A only. The building is a concrete frame structure with post-tension slabs, stability shear walls, and pile foundations. It contains an open ground floor parking, 3 levels of apartments, and 1 roof level for plant equipment. I obtained elemental concrete volumes of the superstructure, which consisted of slabs, walls, beams, and columns, and the substructure, which consisted of pile caps and piles. Again, this is a simple task and takes less than an hour to complete, depending on your building scale. At this stage, I use reinforcement estimates based on the volume or area of concrete to obtain the total rebar tonnage. For the post-tensioning cables, I used a reinforcement carbon factor for the calculations, as I did not have a readily available PT carbon factor. Next slide, please. Once I obtained the material mass of the structure, I used a spreadsheet produced by Arup called PEC to apply the carbon factor calculation. This is one of many tools available, but is not required. The calculation remains the same. At this point, I added some additional structural steel masses for canopies and walkways. Next slide, please. I calculated a total carbon tonnage of 856 tons and divided it by the GIA, which resulted in a value of 320 kilograms of carbon per meter squared. On the right, the data is reflected in pie charts for context. The first pie chart indicates the distribution of carbon tonnage I have 56% for concrete, 42% for reinforcement, and 2% for structural steel. The second chart has the material mass distribution. I have 96% for concrete, 4% for reinforcement, and a negligible amount of structural steel. Just from this data, I can see that just 4% of structural steel contributes to 44% of carbon tonnage due to its high carbon factor. Sorry, just 4% of steel in total contributes to 44% of carbon tonnage. Next slide, please. I can now perform the final step of benchmarking and comparing my results. From the graph on the left, a range of values is shown in blue based on past projects. I use that to get an idea of where my building sits within this range. I can see that I am within this, and I can now add my volumes to the same database to shape the range further, which is what our goal is, to basically benchmark against real life projects. I also use the scores rating system on the right, where I can see that my building falls within rating E, which aligns to a typical mid-rise building. The next step for me is to adjust and track my calculations at different project stages, with the attempt to continuously reduce the impact the building has by making smart material and design choices. I just want to reiterate that the calculation is quite straightforward and makes the most impact when done right at the beginning. Thank you. Now I'll hand you over to Tessa.
Thanks, Suvarna. I'm trying to figure out how to start my camera, but I have no idea how. Start video, there we go. Okay, thank you. So I'm going to be talking about the importance of a country-specific carbon factor. As Suvarna mentioned, she used UK-based factors in her calculation because they were readily available. So it looks at this stage of the workflow. Essentially, we progress from the inputs, which is the design and the volumes of things. Then we do the calculation where we apply the carbon factor. Then in terms of the process, we look at the output, which is what Suvarna has described, and then conduct benchmarking. What's really important as part of this is this iterative process over the design process. So as we get to benchmarking, we can understand where our embodied carbon per square meter sits against other similar buildings, and we can actively seek ways to reduce the carbon in the building iteratively over the design life. So what we're going to focus on now is the calculation aspect and looking at local carbon factors. So a carbon factor, as a piece of jargon again, is the factor that's applied to the energy use or emission to understand the equivalent carbon emissions that are associated with it. And again, I just want to reinforce that this does include not only carbon, but nitrous oxide, I can't remember all of these things that are here, but it's a whole bunch of greenhouse gases, essentially. They're always reported, however, as CO2e, which looks at the carbon dioxide equivalent. And this is looking at a quantified indication of the contribution that this material makes towards the global warming potential associated with greenhouse gases. And then another step in this process is looking at a life cycle assessment, and that's an accounting of the environmental impact. But again, we're looking at embodied carbon, so I'm just going to skim through that. So key messages for this are that the carbon factors that we typically use and that are available in South Africa are largely generic. They can be UK based, they can be US based. They are internationally aggregated carbon factors. Thus far, we do not have any local carbon factors for any specific country, or in fact for the continent of Africa, that are available. If we consider that Africa has 54 countries, there's quite a lot going on there with a lot of regional variation. So these generic factors have been created by structural engineers and interested people around the world. A lot of academics contribute to this. Equally, the building industry contributes to these carbon factors because many of the building industry, many of the industry colleagues, they actually prepare things which are called EPDs for the various products and materials that they sell. And that means essentially that they go through the process of calculating the carbon factor for their specific product or material. So essentially, this takes into account where the specific material or product came from, what is the source of that, and all the transportation involved in its movement and its processing until it reaches site. That's what we're looking for. That is what the carbon factor looks at. So in terms of the difference between using aggregated or international carbon factors versus our local carbon factors, I just want to reinforce Suvarna's point that she made earlier, which is that the most important thing is to start the calculation. Because just even by using these global carbon factors, you can still understand relational improvements. So as you go through that iterative process and identify ways to reduce the carbon in the building, through doing the calculation and assessing that, you will see if you're saving carbon. In terms of the carbon factors, international versus local, they are generally comparable. So the differences tend to be related to transport. So for instance, if we in South Africa are mining the iron ore, sending that to Australia for processing and converting into steel, and then shipping that back to South Africa before it's then processed again, before it's then installed in on a building, all of that transport will add to our specific carbon factor for South Africa. Whereas if it was all done in Australia, for instance, that carbon factor would be lower. Another factor that does tend to differ between local and international carbon factors is the grid energy supply. So if you are using a fossil fuel-based electrical network and grid supply to do any of the processing that's required, then that would carry a higher carbon emission as a result. So whereas if it's entirely renewable or largely renewable in the energy mix, then your carbon factor would be lower. So what we tend to see is that steel is similar across the world. However, there tends to be quite a bit of variation between products such as bricks. So masonry units tend to vary quite a lot. Timber also varies, but we must remember that timber, because of its property as a renewable resource, the sequestration that's attached to that product during its growth cycle is significant. So even when we add transportation onto that, the carbon factor of timber is still very low. The key message here is that we need to actually understand what the material value chain is for each of the products in country, because we can start to apply best practice and use our own engineering judgment to make to choose and decide on ways forward in support of embodied carbon calculations. As we all start to conduct these calculations and the process becomes more familiar and really it should just be something that we're doing at every stage of the design process, then the importance of the local carbon factors becomes more obvious. So that's looking ahead now into a few years' time. When things start to become very, very granular, and especially when we start being able to benchmark carbon factors and the embodied carbon of our buildings across the country, that's when the country-specific carbon factors will become particularly important. And I just want to reinforce again, without having these local South African carbon factors, that must not be a barrier to conducting the calculations. Okay, on that note, I'm going to hand over to my colleague, Fiona.
Thank you, Tessa. So Arup, hi everyone. Arup, as part of their internal research program, have invested in 2 studies to better inform our drive and commitment to low carbon building design in Africa. The aim of the study was to establish and validate a set of location-specific carbon factors, as Tessa has just mentioned, for common construction materials. We focused on 4 countries where Arup currently have offices, namely Kenya, Mauritius, Nigeria, and South Africa. Next slide, please. The first part of the study involved investigating and collecting as much data as possible about typical construction materials in these different countries. The aim was to find out where these materials came from, how they are produced, from the raw material extraction phase to the final product, including all inputs along the way. We reached out to both the private and academic sectors. The second part involved developing and validating a bespoke methodology to create these location-specific carbon factors, quantifying the carbon involved from the manufacturing processes and the research information gathered in study 1. Next slide, please. I keep clicking. Sorry, I didn't realize there was a... There we go. Thank you. The bespoke methodology that we developed in study 2 was centered around 3 different ways to calculate a carbon factor, depending on the information available. These consisted of a location-specific factor, a blended factor, and or an energy-tailored factor. Next slide, please. Our guiding principles throughout the study was to remember that data collected needed to be from the correct/appropriate geographical region. We needed to remember that data collected should be representative of current technologies and processes used. Considering future technologies was not recommended during our study. We needed to remember that our data needed to be recent and that thus far, the factor calculated is an estimate and it is a start to our carbon journey. We needed to list all assumptions along the way and needed to note our level of accuracy when reporting any factors. We also needed to remember that this was an iterative process and that we couldn't get a perfect factor first time, and that it is something that will need to be developed along as we continue this journey. I'll now hand over to my colleague, Maureen, who will take us through Nigeria's specific outputs from our study too. Thank you.
Thank you, Fiona. Good day, everyone. Okay, so talking us through our experience developing local carbon factors in Nigeria, I'd just like to highlight before going in that what Suvarna took us through earlier was embodied carbon calculation on projects. But then what I'm talking about now is calculating the carbon factors used in such calculations. So for us, we started the study with some desk studies and stakeholder identification. So basically trying to see who was doing what with regards to embodied carbon calculation in Nigeria, and just generally see what information was available and identify who we could speak to and ask questions going forward. And then we moved on to the data gathering and stakeholder engagement stage. And this basically involved understanding material flows and the supply chain of materials in Nigeria generally, and also asking stakeholders about their existing environmental products declarations or any sort of life cycle assessments that had been done. We didn't find much at this stage, but then it was interesting to use the stage to sort of gauge the awareness level of stakeholders and see which ones were enthusiastic to partner with us on the study going forward. We then attended the carbon factor training, which was organized within Arup, which basically took us through the 3 methods of calculating a local carbon factor. And through this training, we were able to decide that we were going to use the energy-tailored method of calculating carbon factors, since we didn't have a lot of figures or local data to use the other methods. And so we went on to calculation and comparison with the carbon factors calculated from other African countries. And then we went on to learning about different carbon tools to plug in these carbon factors, or even to use already verified carbon factors. One of such tools was the PEC, which Suvarna took us through earlier. And then the stage we're at now is carrying out trial calculations on our projects and just trying to get a picture of where we're at. Next slide, please. Okay, so the specific materials which we calculated carbon factors for in Nigeria are steel, concrete, blockwork, aggregate, and timber. And from this engagement with stakeholders, apart from being able to get a bit of specific information on these materials, we're also able to learn about the plans which these stakeholders had with regards to introducing more sustainable materials, replacements for ordinary Portland cement, and so on. Next slide, please. And so going into the calculation proper, what we did was to refer to existing databases of information. So for the A1 to A3 and A5 stages, to calculate the carbon factors for those stages, we made use of UK carbon factors as well as UK grid emission factors. And thankfully, we were able to find grid emission factors for Nigeria. And so it was just a case of using simple simultaneous equations to then derive carbon factors for these stages for Nigeria. And then moving on to the A4 stage, which was primarily about transportation of these materials to site, what we had to do was to refer to the I-Structy guidance document on transport emission factors for different modes of transportation. And then we, based on assumption and based on experience on various projects, were able to calculate typical distances that materials would travel within states in Nigeria and across states in Nigeria. And we then used these figures to calculate the carbon factors for the A4 stage of projects. Next slide, please. Okay, so this just shows a summary of our feeling towards what we were able to get from the study. Generally, as I said earlier, the most exciting part was getting to engage with people within the space and having a feel for what their understanding was and what their enthusiasm level was with regards to reducing carbon emissions from the industry. One thing that we would definitely look to doing much better in future, or that we would advise anyone looking to carry out this kind of study, is to first test the awareness level of stakeholders, try to upgrade the awareness level of stakeholders, and then ask the necessary questions. This would most likely reduce any reluctance that the stakeholders may have regarding providing information that would help in your calculation. With regards to the confidence that we had as at the time we carried out this study, the confidence we had in the carbon factors calculated was not so high, but then that's primarily because as at that time, we were focused on getting location-specific data, which we did not get. But then as Tessa and my other colleagues have mentioned earlier, what's important is using the carbon factors that are available and ensuring that the carbon emissions are indeed being reduced on projects. Next slide, please. Okay, so just a run through on one of the projects that we have used the PEC tool to calculate the embodied carbon. This project is actually the Office of the National Security Advisor in Nigeria here. And although the project already has a lot of sustainability gains with regards to reducing the amount of energy required for cooling and so on and so forth, we then explored how much gains we would have had on carbon emissions if we had considered embodied carbon at the start of the project. We did get our results, and we found out that when compared to other structures of similar kinds, the embodied carbon was actually significantly higher. And so going forward, we'll be looking to compare our new designs to that project. So benchmarking our new designs to that project and making sure that we're reducing with reference to that project. Thank you very much. I'll now hand over to Alex.
Thanks very much, Maureen. Hi, everyone. My name is Alex. I am a structural engineer at Arup, and I'm based in Cape Town. Today, for my part of the presentation, I'll be covering the current guidance and for our carbon cutting opportunities that are available to us as structural engineers. Next slide, please. Okay, so basically, I just want to give an overview of the benefits of this exercise. So as Tessa mentioned in one of our previous slides, is that the biggest impact we can make for our projects is at the initial stages on the onset of our engagement into the projects. So making these upfront decisions can be vitally important for us to make the biggest savings for the carbon footprints for the structure. So initially, when we are involved into the project, we are presented with a set of plans or layouts from the client or say the architects. And my initial step for the engaging into the project is to look at ways in which we can look at maximizing the structural efficiency of the building. So that would be my typical workflow, exploring various opportunities to look at the efficiency of the materials and to see how we can achieve what we need to, which is aligned to the designer's intent. Next slide, please. So the initial assessment, when we receive the layouts from the architects, would be looking at the materials that we're going to be using, for instance, the grid spacing of the building, and also the geographic location-specific items. So understanding the context of the design is important to understand what is looking to be achieved. This would be the point at which I would start at with to see what the architect is looking to achieve, and then how we can rationalize the design and present new ideas for them to look at to see if we can achieve a better structure still in line with their design. Past examples of this would include basements, for instance, where we've had projects where the architect is looking to introduce a new basement in a specific area on the site to provide access for two different areas, and this can easily be omitted by transferring access stairways to various other locations on the site, or retaining structures if we receive a geotechnical report and we can see that the angle of repose of a bank doesn't need a retaining structure, then we would normally present this to the client or to the architect to see if we can achieve it without actually introducing additional structure. And on one of our most recent projects, we've introduced a rock store, which is essentially a heating and ventilation assisted system to achieve a better energy rating for the building. But that's essentially a room full of rocks and a very heavy structure. And on that particular project, the architects actually wanted to present the space on a suspended structure. And this was an immediate red flag for me, where I asked the architects, can we move this to another area which is on grade? And this proved to be a significant saving for the building. And these are typical sort of steps that I would undertake right in the beginning of the project, where we can look to really make a big saving to reduce the carbon footprint of the structural materials. Next slide, please. So one of the biggest opportunities for us as the structural engineers is the use of the materials. Typically, I like to look at use the system of the 4 Rs: reduce, reuse, recycle, and recover, and apply this to all the materials across the site. So for instance, initially we would look at limiting the carbon intensive materials. As you saw from Suvarna's presentation, that concrete and structural steelwork has a significant effect on your embodied carbon units. So if we can look at lowering the carbon intensive materials, this would prove to be very beneficial for us, as well as choosing lower carbon alternatives and sequestering materials. So for instance, timber, if we can see that it's historic, based on its historic data, we would preferably go for that if we can. Obviously, there's instances where this isn't achievable, but then we could look at the EPDs of the material to see to use that data to get a better informed decision of what materials we can use. So this would basically carry on to look at the local materials to cut down on the transportation costs, fewer finished materials. So for instance, an example of that would be to use, for instance, polished concrete, where this carries a lot of weight in terms of saving on the carbon footprint of the project, and possibly unfinished ceilings. We found that this makes a very big impact on our output. And then as well as the specifying low carbon concrete mixes, so to use a cement replacement as far as possible within the guidance that we've used. So for instance, on one of our most recent projects in Cape Town, we specified Mat 5 concrete and Mat 6 steelwork according to the GBCSA, and this actually allowed us to achieve a 6-star green rating on that project. So that made a very big difference, just to make sure that we're using a very low carbon concrete mixes for those projects. And then another point that I'd like to raise here is the reusing materials where you can. So Arup is busy with internal research to develop an app called DigiYard, which will allow us to more formally reuse materials to make sure that the structural performance of that material can still be achieved. Yeah, so this is a work in progress, and yeah, so this would also allow us to minimize the waste, and as far as possible. Another example of this was the eco bricks that are also very beneficial to use as void formers. So we've used this on past projects successfully, and I would encourage this to, for you to look into this further as well. Next slide, please. So lastly, I'd like to just touch on the strategic design when undertaking your scheme work in the initial stages of the project. So for instance, providing flexible internal space is a key aspect here. This would normally allow for future use to future-proof a building or space to avoid the scenario of demolition, which has proven to be very to make for a very big saving, as well as the reuse of buildings and spaces. So this was touched on previously as well. To build less and minimize demolition, we are always looking for opportunities on new projects where we've got an existing building to maximize the repurpose of that structure as opposed to demolition. And another component here is the prefabrication of elements as opposed to on-site work. This normally cuts down on your wastage, and there's a better component of QA as well. And lastly, to design for disassembly. We've seen this becoming quite a predominant factor in our design these days, with steelwork being designed for disassembly, where we can reuse the structures in the future as well. And lastly, I'd like to just encourage you to explore these options, and as structural engineers, we can make a real impact on the work that we carry out. Yeah, thanks very much. I'm going to transfer back to Tessa. Thank you.
Thanks, Alex. So I'm going to end off with a little bit of a conversation around next steps and what we're trying to do and what we as an industry need to be doing. So the first thing is just, I think that there's an opportunity for confusion between certification tools and embodied carbon calculations. So as it stands at the moment, most certification tools, and certainly none that are available in South Africa, actually account for embodied carbon. The EDGE tool that's being promoted by IFC, that does include it to an extent, but it's quite simplified, and we can have a separate conversation about that. It's worthwhile, but it's not very in depth. So, but we need to be very clear that there's a distinction between a certification tool, which is used by, for instance, the Green Building Council of South Africa, and embodied carbon calculations. Embodied carbon calculations stand independently of that, and is a process and a tool that every single structural engineer ideally should be using throughout the design process, irrespective of if the building they're working on is seeking certification or not. Okay, so at the moment, the Green Building Council of South Africa are seeking to create a credit that looks at embodied carbon within their net zero tool, but that's a work in progress, and that may only come out in a little while. So I just want to reiterate, certification and embodied carbon calculations are different things, and as structural engineers, we need to be conducting embodied carbon calculations often and throughout the design process, irrespective of certification. So in terms of looking ahead, we're working together with the Green Building Council of South Africa, the GBCSA, to understand how we as an industry can be promoting and educating with regards embodied carbon and the need to reduce that in our building design. And so this is a work in progress. It's conversations that we've started and that we're very, very happy to be part of. There is quite a need to be sharing information So the carbon factor calculations that Fiona and Maureen spoke about earlier on in this talk are critical. And the information that feeds those calculations is actually the basis of this. So for instance, what Maureen spoke about is that she was actually using aggregated data to plug the gaps in her particular calculations. We do live in what can be quite data scarce environments. And so what we as an industry need to be doing is actually gathering that data to plug that gap. So we're having a conversation, and the GBCSA, for instance, is really trying to lead on that. And through their credits, trying to become, and we're thinking about how there could be a platform for data sharing, with the goal that this data would then plug the gaps in these carbon factor calculations, with the end goal of then having much more accurate carbon factor calculations or carbon factors for South Africa, as well as other countries on the African continent. So key message from this talk today is please start calculating, don't wait. We mustn't be waiting for local carbon factors to start. As I mentioned before, the calculations are relational and most of the materials are comparable internationally. So using aggregated data is a fantastic starting point, and it's still going to get to a better outcome. There's also a really big need to be sharing information, sharing knowledge. We are not going to get to where we need to get unless we all work together to get there. So we really need to be working together, sharing all of the knowledge that we have, and making sure that as an industry, we are designing the best that we can design. And on that point as well, it's learning from each other. So collaborating and sharing on platforms such as this that the iStruct-D has created is a wonderful forum. And really, I look forward to being part of many more conversations where we talk more about embodied carbon and the lessons that we're learning on our projects. There are some really, really useful links. I know that the principles, if you're not familiar with embodied carbon, like there can be a lot of jargon. I spoke about that earlier, but there are a lot of really useful links available online. So our colleague Will Arnold spoke about the climate emergency last time at the last talk, and he in fact is the iStruct-D's global head of climate action. There are a number of resources available on the iStruct-D website, on both the South African as well as the international ones. So please do use those resources. There are really great YouTube videos as well. So it's really, really good ways to access this information. Equally, the RICS guide, which is a UK-based, but with, it's a process that we're talking about, that is really good as a source for how to do an actual embodied carbon calculation. There's also a document called 10 Things to Do Now, which is published by the iStruct-D. And that, as a structural engineer, gives a really, really, really good overview of where we can have the most impact. And then on to Suvarna's point from earlier, we do need to know how to calculate the gross internal area. So there's a link for how to do that. So I encourage you all to please have a look at that. And on that note, thank you for inviting us on this platform.